our next speaker is Arash Pourdamghani. I hope I said that right.
Yeah.
And he's advised by Stefan Schmid, who's at TU Berlin, and apparently also maybe still in Wien. And he'll talk to us today about SeedTree, a dynamically optimal local self-adjusting tree. Go ahead.
So hi everyone from Berlin. So today I'm going to talk about a paper that has been presented in InfoComm 2023 months ago. This is a joint work with my supervisor Stefan Schmid and also Robert Sama and Chen Avin. So hope you enjoy. So first of all, let me give you a very high level view of the SeedTree, and I mean in a fun way, let's say. So let us assume that you sit at the root of this tree and you want to send some request to get the contents of the fruits of the tree. And so for you, it would be nicer if those contents of these fruits, or what we call seeds, would be closer to you. So what we want to do here in our data structure is that we want to look at the demand, at the incoming demand, at the request, and self-adjust these contents of these fruits such that when something is accessed more often or more frequently or more recently, then you can access those contents faster. So this is a very high level view of what we are going to talk about, and the rest of the talk is deciphering what I told you right now. So first of all, I want to talk about why we worked on the SeedTree, and then I will go what is SeedTree and how we proved its dynamic optimality. So first of all, about why, I would not go very deep into why we designed SeedTree because my supervisor had another talk, I think a while ago, a month ago or so, in a similar seminar. So he talked more in depth about why we are going to design self-adjusting trees and networks. I only go over what I need for this talk. So let us assume that we have a set of servers, and in these servers we have a set of virtual machines, and these virtual machines want to communicate with each other. And they, for example, we have a machine learning application, and we divide the process into different servers, and then they want to communicate with each other. And there is a network on top. And then we want to see how we can make this communication faster. So this is one of the applications that we can think of. And why we are talking about demand awareness and self-adjusting, why does it make sense to, I mean, we want to see if we have any structure in these demands and requests. So one observation that have been done recently from a set of data sets from Facebook and others, that in the demands between different servers, we have two types of structure. First one, we have this spatial structure, which means that some items or communication between some servers is more often, it happens more often, so it's on this dimension. And we have another dimension in the demand, it's temporal structure. It means that communication between two virtual machines or two servers would happen again and again and again in a short period of time. So if you see a communication between a pair of virtual machines, you probably would see it again right after, and so on. And we see, for example, in neural network applications, we have both spatial and temporal structure. And the final hope of my PhD thesis, or the project that we are running with Stefan, is that if we can build self-adjusting networks that utilizes these demands and can perform better, given that the demand structure is not uniformly at random. In this talk, I mean, this is a hard question. We have multiple papers on it before, and we are also working on a couple of papers in the upcoming years. And here we want to answer one question, that if we can have a dynamically optimal self-adjusting tree. So our vision is that we can somehow overlap or combine these trees to get the network that we want at the end. But let us start with a small and simple question, is that how, if we can achieve a dynamic optimal self-adjusting tree.
Arash, what was the y-axis, so spatial structure? So what happens as you go up?
So it means, I mean, when you go up, you don't have these frequent items. So the items, they are distributed uniformly at random. So, but here, for example, when you go a bit lower, it means that you have some items that are happening more frequently, or you have some communication between servers that are happening more frequently. When you see the total demand, then you will see these communications much more than the others. So it's not a temporal, or it's not dependent on time. It's dependent on when you look at the whole demand and you see, okay, these communications happen more often. So this is this dimension, and in this talk we are mostly interested in this temporal structure of the demands. And I mean, there were previous works or on that focused on this spatial structure. Did I answer your question?
I think so.
So now let me dive into what is SeedTree. So here, as I said, we want to focus on the tree, not on the network. So we are only considering single source communications, and for now we forget about communications between that are initiated from other servers. And here we have a vision that we want to also add to this single source communications. We want to have local routing. By that, I mean, we don't want to store the information that, okay, from this source to this destination, we need to take this path. We want to say, okay, if you have a request for a virtual machine, and then you have the address of this virtual machine as a destination, then you can do the routing only based on this address, and you don't really need to keep storage for the routings between different sources and destinations. And what we do, we assume that there is a tree, a binary tree on top of these servers, let's say. And then what we can do here, essentially, we can, the operations that we have is moving items on a link, so or servers on a link. So you can take a server, and with cost 1, you can move it, or you can also do the search, and then with cost 1, you can access an item. But I mean, we have different variations that this cost might be unproportional. So the cost of reconfiguring might be a constant factor away from the cost of access. But for now, let us assume that the cost of reconfiguring and moving an item between 2 different servers and the cost of looking for an item and traversing the edges would be the same. But here, I mean, it's the other aspect that we want to look at in our work that prior work might not really covered in the terms of the binary trees, is that we have a capacities in the servers, and if we move this item, let's say, to the root, then this the server might not have enough capacities. So maybe we want to move some item out and bring this item out of the server. So we also would end up with a good load balancing on the servers as well. And so this would be the final configuration after the readjustments. So for now, I mean, I will only talk about these abstractions, that we have a set of servers and we have a set of items, and we have this binary tree built on top. Another point that I wanted to make, I mean, you can go beyond binary, you can go to any constant degree, but again, for simplicity, let us look at the binary trees right now. So to reiterate on the formal model, we assume that we have a set of servers connected as a binary tree, and each server has a capacity C, a fixed capacity C per each server. And we have a set of items that comes over time. We don't know the whole request sequence. And these requests are accesses to items, and we might have repeated accesses to the same items again and again over time. And the other thing that we wanted to do is that we want to only have this local routing based on the IDs. So for example, here, based on the last bit, we can say the last bit is 1, we will go to the right, and then the next bit is 0, we will go to the left. and then we can put this item here, for example. And I mean, this talk is about the access operations, and we assume that we already pre-filled the server. The insertion of the items is not so hard. If you can access an item, you can essentially transform it to insertion as well. So we assume for the rest of the talk that we have a pre-filled server, and we want to do two operations. We are allowed to do two operations on them. First one is the access. So we will go and look for an item. And as I said, the cost of traversing one edge when you are looking for an item is 1. And the other operation is reconfiguration. So it's moving one item from one server to the other. So this might be something that, yeah, it's a bit different. The way that we reconfigure, that define reconfiguration is a bit different from other traditional self-adjusting binary search, self-adjusting binary trees. And the measure that we want to optimize or minimize is the total cost, the access cost plus the reconfiguration cost. And our goal is to achieve dynamic optimality. It means that the cost of our algorithm would be only a constant away from the cost of the optimal offline algorithm. And just to recap on the related work, this is the work that we have done. We show that it's dynamically optimal and it provides local routing, and our operation is the item movements. A set of other famous related works are splay trees, tango tree, and multi-splay, which is an extension of almost both of them. And what I mean, probably you have heard about this conjecture of dynamic optimality of splay tree. We don't really know right now. What the good thing is that we have the local routing, and the operations that they used there was the rotation operation. But other people have also tried to think about other types of self-adjusting trees. For example, we have this adaptive Huffman, but the operations there, I mean, I would assume it's a bit unrealistic because you need to swap a set of subtrees. And recently, work which was similar to our work, but it didn't have this local routing. And it also didn't have the capacity. When you have for configuration, you needed to swap two different items from the neighboring server. So there are a bit more works on this self-adjusting trees, but these are the selected works that we wanted to show different operations and what we can achieve with these different operations.
So Arash, can you say why the limited reconfiguration model that you're looking at now is sort of more realistic than, I guess, being able to do things like rotations? Is that because you would have to physically rewire,
So one thing that I can go it at the end if you like. So we have these optical switches, and what we can do essentially is that we can transform these movements to the matching model. So when you have a movement of the items, you can essentially change the matching, and changing the matching is very cost efficient for us given these optical switches. So with optical switches, you don't have the static infrastructure on top of the servers, and then you can also adjust the links on the fly. And we showed in the paper how we can transform our model to this matching model. I have backup slides at the end. I will go over them if you like. But this is also one part that we are looking. Despite this virtual machine transitions, the other application that we are working on is this using optical switches and transforming our model to the model that would be feasible for the optical switches.
But even without optical switches, I think your model makes sense, right? I mean, you just move items or whatever chunks of information that one server has to another server.
Yeah.
Like across an existing link. Okay, good. Thanks.
So I want to now go a bit deeper into our algorithm and how we analyzed it. So the first thing that we did when we wanted to design this algorithm is that.
Can I just ask, like, how do you measure the quality of your algorithm? Like, what's the, like, how do you measure the running time? It's the number of operations?
The number of accesses. So I mean, when you traverse an edge, it could be an access, and this could cost 1. And when you do these moving the items one edge, this is also cost 1. I mean, in practice, this reconfiguration might be more costly. We also included that in the paper, that it might be C times the cost of the access operation when we are looking for an item. And our objective is to minimize this total cost of the two operations. So we want to have realistic number of reconfigurations such that we also reduce the access cost.
Right, thanks.
So what we've done to design our algorithm is that when we are given these items, the keys, let's say, we will hash them to another set of IDs, and then we use these hashes. These hashes might be much longer. I will only use the first 3 bits for visualization here, and we use these first 3 bits, or we use these new addresses that are generated by any hash function, but let us assume that we have a hash function that can generate uniformly random. In our simulations, we use the realistic hash functions that we have, but for the analysis, let us assume that we can get a uniformly random output. So this is one thing that we did when we are given the keys, we just hash them to a new set of keys. And the other assumption that we did is that I will tell you in a second why we need this assumption, is that we don't really fill all the capacity of one level. So if we just use a fraction of the capacity, this fraction can be almost 1, but not exactly 1. We use the fractional occupancy per level. So we will make sure that in each level there is a, let's say, half. I mean, you can go much higher than half, but let's say half of the capacity is used, exactly half of the capacity is used at any point of the time.
Sorry, the load level initially, like you can't remove or add items, right? You only move them around. So I mean,
we can also, sorry, go on, sorry.
I was just like, if the tree starts out completely full, like how do you change anything from there?
So I mean, we can also add a level. I mean, this would be an additional level to the tree. If all these levels, they have all their fill with their fractional occupancy, we will just add a new level in the tree, and then we will go on from there.
Okay, so you can even add nodes in this model. I didn't.
Yeah, I mean, so for example, here we have this empty node server. Let's say we don't really. It's not there. I just show it for visualization, and we might later on use it, and then we can add another node. So we don't really need to have complete full levels. We can have partially used levels as well.
Okay.
So what happens when we have the access? We will do this local routing based on the IDs to find the item. So we go right here. And now, because we wanted to have this property of the demand awareness, we want to bring this item to the root. So but that's what we are proposing, is that if you pull up this item to the root, that would help us with the dynamic optimality. And then, but here, I mean, you will see the fractional occupancy of this level is violated. So we need to bring back an item down to the same level that this item was taken from. So we will find an item in a level and then pull it up to the root. And after that, we will select an item uniformly at random at each server. So in this server, we will select an item uniformly at random and push it. So we select this 0, 0, 0, let's say, and we push it one level down. Again, we will select an item uniformly at random and we will push it one level down. But what might happen is that we might have full servers that we cannot add any item, so they already at capacity C. Let's say here the capacity was 2, so it's already at capacity, and this attempt failed, so we will revert this attempt and try again. So we will select an item uniformly at random in this server. We will push it down. So here the uniformly at random gave us another item, and now we have the server that it would go down to. It has capacity, so that's fine, and we are happy, and everything is done. And in the same level, we have again the same fractional occupancy. So we bring back this constraint that we wanted to have. So that's the whole algorithm: pull up and push down. Is it clear? So now we want to analyze it, and we want to show that our algorithm is dynamically optimal. It means that it's constant competitive. So we do it in 3 steps. The first step is that, okay, we don't do crazy reconfigurations. The reconfigurations is bounded by the access cost. And why this formulation is that we need to do the access and pull up the item. So this is why we have this one here. And here, this comes from the fact that how many times we need to do these attempts again and again. And it turns out that it depends on the fractional occupancy. So if a level is more full, I mean, it's natural that you probably would face more full servers, so you need to do it again and again. And the good thing about our algorithm is that it never fails, because in the worst case, worst possible scenario is that you just bring the item that you pulled up. So you bring this purple item back down. So your random selections would bring the same item down. So our algorithm never fails, and the number of attempts that it needs to do is proportional to the fractional occupancy. So this is one step and the proof sketch of what we get this property. The other thing is that we look at a middle step tree. So this is not a realistic tree. We just use it for the analysis. We assume that there is a most recently used tree. What we mean with most recently used tree, it means that it puts the items based on the level of the item would be proportional to the time that they have been accessed. If they have been accessed more recently, they are closer to the root. So we assume that there is this hypothetical tree, and we show, okay, access cost of our algorithm is not much further from this MRU tree. And intuitively why this happens is that, okay, I mean, we brought this most recent used item to the root, so that's it. And when we are pushing down, because because of this randomization and because of the fact that we have more servers to choose item, and inside each server we have this capacity C, so the probability of any item to go down would decrease when we go a level down. So that's why the level of an item in our tree is proportional to the level of the item in the most recently used tree. So this is the second step. And the last step is that we want to show that this access cost of this MRU tree is proportional to the optimal offline algorithm. And what we do here is similar to the classical things that I have for the least access. But the difference here is that in the least access, you will compare the least recently used algorithm or your algorithm with the optimal algorithm. But we have this intermediary MRU algorithm, and we define inversion as if an item, we define an inversion between two items, these two tuple items, if we expect one to be closer to the root, but that would not be the case. So it have been accessed more recently, but it's further away from the root. So we define this as an inversion. And the good thing about MRU tree is that it doesn't have an inversion by definition. Then we only have inversions for the opt, and then we need to analyze, okay, what per movements of the opt and per movements of this MRU tree, what changes in the potential function, and how, and then based on these changes, we can get the amortized access cost for MRU. Then, I mean, basically the competitive ratio would be just a multiplication of these three factors that you see on this slide. So we get the +1 for the access of the SeedTree, and that would be it. So we have, with these three steps, we can get the constant competitiveness that we wanted. And we tried our algorithm on two different data sets. We generated a data set ourselves, and we showed that, for example, when we have the more temporal locality, when items are accessed again and again more often, our algorithm outperforms the static or oblivious algorithm much better. And we also, you look at the Facebook data set, and then we wanted to see the effects of, for example, capacity. We have other plots in our paper, but for example, here we saw that it would go down a little bit, but probably around 8, the capacity around 8 would be fine for us. So in summary, we introduced the constant competitive single source self-adjusting trees, and we showed how this, with this randomization, we can avoid these failed attempts and also avoid congestion in each node. And this, I mean, this notion of capacity, I think this was something new. We haven't seen it before, and it was, yeah, maybe a feature of our tree. And later on, as I said, we want to go to the networking model, and we are working on the practical deployment. And as the trend is today, we want to also maybe discuss to analyze it, considering an oracle which gives us advice about the future request sequence. So thank you very much. And I think I was more or less on time. So thank you. And please feel free to check the full paper, our website, and my personal website. Thank you very much. Okay, Peter, I saw that you raised the hand.
Yes, thank you for your presentation. Am I hearable?
Yeah.
Okay. Can you explain me whether I've understand it correctly, that your entire analysis is from the perspective of a single process, basically?
Can you
issuing the request? Because if I look at the initial picture where you have this collection of servers, there are many processes running on them, each generating requests which may be entirely incompatible mutually. So is your analysis based on a single process perspective?
Yeah, I mean, it's based on the single server perspective. So I mean, the instances that are the requests from instances in a server. And as I said, we know that eventually we want to go towards what you said, that yeah, different instances might have different requests and they might be incompatible with them. So yeah, that's the challenging part. We suspect that we have a way to combining these trees so we can address your concern. But this work is, as you said, it's from point of view of of instances in a single server.
Okay, thanks. That was what I didn't get. Thank you.
I have a couple questions. So first, in your model, is the adversary oblivious? Or
So,
is it with respect to like something that can be adaptive to your randomness?
so yeah, I mean, we assume that, yeah, we do this random, we are given these items IDs, and then it's oblivious about the what happens in the tree. So it can knows about the algorithm, but it doesn't know about the random choices that we.
Yeah. And the second thing is that this capacity, so is this a parameter that like is somehow a function of the initial instance? Like this is like how loaded the system is at the beginning, or is it a tunable parameter? Like
So we
as
assume
part of
that the designer of the system will say, okay, my server has capacity 10. It can occupy 10 virtual machines at most. So we consider
sorry, I meant the F. I mean this like
the fractional occupancy. Then
sorry, yeah, right. So is the F somehow a property of the initial instance and it stays the same over the all of time, or is it something that is like a parameter of the algorithm or that you have some control over?
So yeah, I mean, if we have an initial instance with a certain F, then from that point on, we will keep using the same F. So, and the algorithm would keep the same F throughout the its
Right. So that means if the system starts sort of more loaded, then like your competitive ratio gets worse. Is that correct?
Yeah.
Yeah. Okay. Interesting. All right. That was what I was trying to understand. All right. If there are no more questions, let's thank Arash again.